Welcome. So this is the first lecture after the module overview. The first lecture, we are going to look at the number system. Okay, the number system. This is just the chapter 1, the number system. Okay, so mathematics is its own language. Here now we are using letters of the alphabet to represent different variables or unknown. And when we are using these letters of the alphabet to represent unknown, we call that algebra. Okay. But generally, before we do that, we want to look at the number system that is used in calculus. Okay. The numbers comes in different types, or what we call sets. Okay, so the first type of number is called a natural number or a counting number. A natural number is denoted by n, a capital letter N like that. So if I say x is an element of n, I mean x is a natural number. And natural numbers start at 1, and it only includes integers like 2, 3, 4, 5, going upwards up to infinity. So they are also called counting numbers, because if I ask you to count something, you start at 1. You say 1, 2, 3. You don't start at 0 when you're counting. You start at 1. Hence, this group of numbers is called natural numbers. Okay. And then we go to integers. Integers is another group of numbers. Integers now includes what we call negative whole numbers and 0. So 0 is also an integer. -1, -2, -3 are integers. But these numbers are whole numbers. Okay? Just like natural numbers are whole numbers, integers are also whole numbers. So integers, they start from negative infinity, then come down to -10, -9, -8, -7, -3, -2, -1. Then we have 0. Then we start to say +1, 2, 3, 4, going upwards up to positive infinity. And in these integers are denoted by a capital letter Z. Okay. So integers, they start from negative infinity up to positive infinity. And from -1 going to negative infinity, they are negative integers. Then from 1 going to positive infinity, they are positive integers. Then 0 has no sign. It's neither positive or negative. And positive integers are natural numbers. Okay. So when we talk about natural numbers, we are talking of positive integers. You can see that positive integers are a subset of, or to say natural numbers are a subset of integers. Okay. Then another group of numbers that you should know is called rational numbers. Rational numbers is any number. The definition of rational number is any number which can be written in the form P over Q, where Q is not equal to 0, and P and Q are elements of integers. Okay, so P and Q are numbers that we defined above as integers, are these numbers. If you are able to write any number in this form, P over Q, where Q is not equal to 0 and P and Q are integers, then that number is called a rational number. So this is the mathematical definition of a rational number. And rational numbers are denoted by a capital letter Q like that. So if you are able to write a number P over Q, and P and Q are integers, and Q is not equal to 0, then that number is called a rational number. Therefore, it means all integers, since 4 can be written as 4 over 1. Like if I talk of 10, 10 can be written as 10 over 1. Therefore, and also, like for example, negative numbers like -100. -100 can be written as -100 over 1. As long as P 3 is an element of integer. You can see here we've got minus 100 and 1 is also there. We also have 1 there. It means all integers are rational numbers. But there are special rational numbers where the denominator here, where q is equal to 1. When q is equal to 1, we form an integer. But does not mean that these are the only rational numbers. We also have rational numbers like 2 over 3 that have got a denominator q here not equal to 1. We also have minus 5 over 4, minus 20 over 3, minus 70 over 10. They are all rational numbers. As long as the numerator and the denominator are elements of these integers and the denominator is not 0, then that number is a rational number. But can you see that all integers are rational numbers? But there are special rational numbers where the denominator q here is equal to 1. Okay, so which means, but all integers are rational numbers. Are we together? Then we also have the opposite of rational numbers is called irrational numbers. Irrational numbers now are numbers which cannot be expressed in this form. Examples of irrational numbers includes numbers like pi, and also a natural logarithm, which is exponential to the power 1, the Euler constant, and also we have got square roots of all non-perfect squares are examples of irrational numbers. Like, I mean, if I ask you to express square root of 2, square root of 3, square root of 7, square root of 10, pi, those numbers cannot be expressed in this form, p over q. Therefore, they are called irrational numbers. Okay. But when you combine irrational numbers and rational numbers, you form what is called real numbers. Real numbers now include irrational numbers and rational numbers. Okay. So a set of all decimals, both the terminating and non-terminating decimal. Okay, so what about another important thing that you should know is that rational numbers, the one that we discussed above, can also be expressed in another form, which is called the decimal form. Okay, so when rational numbers are expressed in decimal form, like for example, we can have numbers like 2 over 3. We can say how many times does 3 get into 2? 0, comma. 3 get into 20, that's 6, remainder 2 into 20 again, 6, remainder 2 again, into 20 again. So when you express 3 over 2, we write it as 0, 0,6666666, and the 6 continues like that. A number like half can be expressed as 0,5. A number like 3 over 4 can be expressed as 0,75. So all rational numbers can be expressed in decimal form, right? And also irrational numbers, which we cannot express as p over q, can also be expressed in decimal form. Now, the difference between the two, numbers like pi, if you punch in your calculator, what is pi? You get a decimal point. The difference now is when you express rational numbers in decimal form, there are two things which happen. It's either the decimal point ends somewhere, like half. The decimal point of half is 0,5. The decimal point of 3 over 4 is 0,75. So it's ending. So we call that a truncating or an ending decimal point. Or we have got other rational numbers. When expressed in decimal form, you have got a non-truncated decimal point. But when the number is a rational number, the decimal point forms a pattern which we can easily recognize. That pattern it means that the decimal numbers repeat itself. Then when you see the decimal numbers repeating itself, we call that a rational number. Okay, then that's now the difference between a rational number and an irrational number. When an irrational number is expressed in decimal point, if decimal point does not form any pattern or the numbers don't repeat, in any, there's no any repetition of those digits that you can see. Okay, so that's what. But when you combine rational numbers and irrational numbers, we form what is called real numbers. Real numbers is a set of all decimals, both terminating and non-terminating. We denote that with a capital letter. So if I say X is an element of R, then we mean it's a real number. And a real number can be a rational number or an irrational number. Right. Like for example, we want to express this decimal, we want to show that this decimal is a rational number. Okay, to show that this decimal is a rational number, we just multiply by, this is what, by 100,000. If you multiply by 100,000, the comma will move to here over 1,000. Since this form is the form P over Q, and P is an element of integers, and Q is an element of integers which is not equal to 0. Therefore, this number is a rational number. Together. So if you are able to express a number in the form P over Q, then it is a rational number. So an example of other rational numbers is this one. You can see that this number, like for example, we discussed the 2 over 3 before, and we see that is 0.6666, and the 6 don't come to an end, meaning that it is a rational number because it has got the digits which are repeating itself. The same thing if you have got M here, you can see 4,275, 19. So this dot means that this 19 is continuous up to infinity. How can we show that this number is a rational number? Okay, since the decimal points are forming a pattern, by definition that I have just given you, it means it is a rational number. But to show that we can write it in the form P over Q, this is what you do. Multiply this number M. We want to show that M is a rational number. Multiply M by 100. So if I multiply this by 100, this side I'll get 100M. This side I get 42751. I get, okay, the comma was here. I get 427,5191919. So this is 100M now. Then I'm multiplying by 100. Why do we multiply by 100? Because there are 2 digits that are repeating itself. So I have to multiply by 100. If there are 3 digits which are repeating itself, I multiply by 1,000. If there is 1 digit that's repeating, I multiply by 10. Okay. So here I've got 100M like that. Then I also write the original M that I have, which is this one. Okay. Then if I subtract this from this, why are we subtracting? You will see the reason why are we subtracting. So if I say 100M, since these 2 things are equal, it means if I subtract this and this, I'm supposed to get the same thing, which is also equal. So if I subtract 100M minus M, I get 99M. The reason why are we subtracting? If I subtract this from this, you see that the 191919, which goes up to infinity, we will subtract each other and we end up having 0. Like for example, here to say 9 minus 9, I get 0. 1 minus 1, I get 0. 9 minus 9, I get 0. So if there are other 19s before, which goes up to infinity in 100M, and I also have M here with 19, these 19s will subtract each other, and then I get 0. Okay, so the only numbers which don't subtract each other, here I'll get 1 minus 1 and get 0. I'll get 5 minus 5. Oh, sorry, okay, all right. So when you're subtracting, you put the commas in line. Okay, so the numbers which don't subtract here, but 1, 2, 3, 1, 2, 3. So I'll get 9 minus, because this 1 minus this 1 will give us 0. 9 minus 5, that's 4. The numbers which don't repeat itself where it starts, that's the numbers which are going to subtract and get a number which is non-zero. Like here I've got 9 minus 5, that's give me 4. Then 1 minus 7, that's 11 minus 7, I give there, that's 4. Then 5 minus 7, sorry, 1 minus 7, 5 minus 2, that's the what I give there is now 3, which is 2. Then 7 minus 4, that's 3. 2 minus 0, that's 2. 4 minus 0. So I now have this. You can see now my 99M does not have numbers which continues up to infinity. Therefore, with this now, I can divide this side by 99. If I divide here by 99, this side by 99, and multiply by, I now want to move this comma, but multiply by 1000. So I can express my M like that. Since M has been expressed in the form P over Q, where P and Q are elements of integers, and Q is not equal to 0, therefore that digit is a rational number. Okay. So we are saying that M is irrational or a quotient of integers. This indicates that this is just there to show you that if you see a decimal which is repeating itself, it's a rational number. Okay, but so sometimes in mathematics, instead of putting those dots at the end of a non-truncating decimal number, we can put dots on top of a number which repeats itself. Like for example, 19 over 6, I can write it as 3,16 with a dot on top of 16. If you punch 19 over 6, you see that is 3,1666. So the dot is placed on top of a number which is repeating itself. The same thing, the M above, instead of writing it as 1919, I can just put 19 and the dot on top of 19 here, showing that these 19 are repeating itself. But if you go to a number like pi, you see that there are no digits which are repeating itself in pi. The pi that you punch in your calculator is not the correct pi, because your calculator have got limitations that it cannot displace digits up to infinity. So your calculator have to round the last digit, but the correct pi does not end. In primary, they say take pi to be 22 over 7. Please note that pi is not 22 over 7 at this level. 22 over 7 and pi are two different numbers. Pi is an irrational number. You cannot write pi correctly. I will give you 100 counter books to write pi. You will be just writing the digits without even seeing the pattern. So these digits are all random. They don't repeat itself. Okay. So we cannot write pi correctly. The only way to write pi is to write it in exact form as pi. But when we want to express pi in decimal form, we cannot do that. Then in summary, there are three types of real numbers: terminating decimal, non-terminating decimal that repeats, and non-terminating decimal that do not repeat. Type 1 and 2, this one that terminate and terminating decimal point that repeat, that's type 1 and 2, are what we call rational numbers. And the one that have got non-terminating decimal point that do not repeat, like pi, square root of 2, square root of 3, square root of 10, they are called irrational numbers. Are we together? Please see that difference. Okay. So a geometric representation of real numbers as points in a line is called a real axis. So real axis, you've got some properties that you are going to look at. Any two real numbers on a line, between any two real numbers on a number line, there are infinitely many rational numbers. Okay. So like for example, if we talk any two real numbers, 1 and 2, between 1 and 2, there are numbers that you cannot write. There are infinitely many numbers, many rational numbers between 1 and 2. Between 1 and 1,1, there are infinitely many numbers. Are we together? There are infinitely many numbers, like 1,11111, 1,000000001, 1,0000. So as long as you've got the decimals, it means they are infinite. You cannot write numbers between 1 and 1,1 and finish them. You need the whole time of your life to write numbers between 1 and 1,1. They are infinitely many. Okay. This leads us to recall rational numbers are everywhere a dense set. This is a property of real numbers. They are a dense set. Real numbers are characterized by three fundamental properties. Okay. So these are the properties now of real numbers. We are now considering all real numbers. And the opposite, if a number is not a real number, is now called a complex number or an imaginary number. Okay. Then can you see that real numbers In real numbers, there are natural numbers, integers, they are all subsets of that. I will explain that later on. Okay, so these are the properties of real numbers. They are the algebraic properties. This means when we have got real numbers, we are able to use rules of calculations, which is addition, subtraction, multiplication, and division, using the algebraic properties. Then real numbers, you've got the order property, meaning that for any two real numbers, we are able to say this one is bigger than this one. There are no any two real numbers which we cannot say, two different real numbers, which we cannot precisely say which one is bigger than the other. That's the order. That's the order. If Man U and Man City play and they score a certain number of goals, we are able to say which one wins. As long as the number of goals they score are different, we are able to say which team wins. So that means there is order. We are able to say which one is bigger than the other. 199, you are able to see that 100 is bigger than 99. 101, whatever two real numbers, there are no two numbers that you can say, not say, we are not sure whether this one is bigger than this one or this one is bigger than this one. So that's order property. They know, the numbers know each other, which one is bigger. Then there's the completeness property. This implies that there are no gaps in real numbers. In other words, we are saying, when you are biomedical engineering students, when you are to measure weight of a patient, you cannot say, this weight I cannot express it numerically or by use of numbers. All weight can be measured, which means there are no gaps. There is no number which you cannot express quantitatively. That's the completeness property, which means there are no gaps. There is nothing that you can say you cannot quantify and give a numerical value to quantify something. Okay, that's the completeness property. Then we go back to the algebraic properties that I mentioned before. The algebraic properties now are further splitted into some other properties, which is called they are now further splitted into properties, which is the algebraic properties of addition. Under addition, we have got the associativity property of addition, which means the order at which we add numbers does not matter. A plus B plus C is the same as A plus B plus C. Adding B and C first and adding A and B first just to give you the same number. Then there is the commutative property of addition, which means A plus B is the same as B plus A. Then there is the identity property of addition, which means if you add any number by 0, you get that number. Then there's the inverse property of addition. For any number, there is a corresponding number that when you add to that number, you get 0. If you add 20, for example, I've got 20. If I add minus 20 to 20, I'll get 0. Are we together? So that's the inverse property. For every number, there is a number that you add to that number so as to get 0. Okay, so these are the algebraic properties of addition. Then we go to the algebra. This is addition and subtraction. Addition is the opposite of subtraction. So we go to the algebraic properties of multiplication. Again, we've got the associative rule. The order at which we multiply numbers does not matter. A times B times C is the same as A times B times C. Multiplying A and B and C, you just get the same answer. A times B is the same as B times A. For every number, if you multiply by 1, you get that number. And there is an X such that if you multiply any number by X, you get 1. Okay, this X will be now the inverse of A. If you multiply a number by its inverse, you get 1. And in this case, this is only true when A is not equal to 0. You don't get, if I multiply 0 by 0, I get 0. So as long as A is not equal to 0, then there is a number that you always multiply another number with so as to get 1. Okay, so now when we connect the addition and the multiplication rules, we get what you call the distributive property, which means when you are multiplying a number and then adding inside, there is now that distribution of distributing A among everything that we are adding inside the bracket. This is called the expanding bracket, A times B plus A times C, which means we are distributing this A to everything that is inside our bracket. Then we have got, remember we talk about the algebraic property and we talk about the order property. Now under the order property of real numbers, we are saying if you've got any two numbers, A and B, which are real numbers, then there is that rule which says that either A is less than or equal to B, or B is less than or equal to A. One of these is always true. Sometimes if A is equal to B, it means the two will be equal numbers, 10 and 10. But if I've got two different numbers, 9 and 10, 7 and 10, there's always that in the which one is bigger. A is always bigger than B, or B is bigger than A is smaller than B, or B is smaller than A. This rule is called the totality of ordering one. Then if A is less than B, it means that B is less than okay, if A is less than B and B is less than A, then it means that A is equal to B. If A is less than or equal to B and if B is less than or equal to A, then it means that A is equal to B. This is called the totality of order 2. It means if we are saying less than or equal to, B is less than or equal to. So in other words, you are saying A is equal to B, B is equal to A, then A is equal to B. Okay. All right, I'm sure you are understanding that we are saying less than or equal to. So if A is 10 and 10, 10 is less than or equal to 10, because 10 is equal to 10. Okay, and then 10 is less than or equal to 10. Then it means 10 is equal to 10. Then if A is less than or equal to B, and B is less than or equal to another number C, then it means A is less than C, is less than or equal to C. This is called the transitivity property. Like if I say 5 is less than 10, then 10 is less than 15. It automatically means that 5 is less than 15. Okay. Then if A is less than B, then if you add a constant, a similar real number to both sides of this inequality, it means the inequality still remains. It means A plus C is also less than B plus C because we have just added C both sides. This is called the order under addition. Okay. If someone has got $10, the other one has got $20. If I give them $50 together, the one which have got $20 will still have the less money than the one which have $50. Okay. Something like that. If you've got $1, the other one has got $3. If I give you $5, both of you, this one which you have $, you still have the less money. Okay. So that's what you're saying. We're adding just a same constant both sides. The order still remains. Then if A is less than B and C is a positive number, which is greater than 0, then if I multiply by C both sides, AC will be still less than BC. This is called the order under multiplication. Okay. Then some useful rules for calculating inequalities. If A is less than B, then C is negative, is less than 0. Then BC will be now less than AC. So here, those years that I did O level, we said you reverse the inequality sign if you multiply by a negative number. That's what you are doing. Here we're saying if A is less than B, then if C is negative, AC will be greater than BC. Are we together? AC will be greater than BC. Then if A is less than B, then the negative of this also is opposite. If I put minus both sides, minus B will be now less than minus A. So if I put negative, a big negative number is a small number. Are we together? If A is greater than 0, then 1 over A is also greater than 0. For whatever real number that you can think of. 10, 1 over 10 is greater than 0. 100, 1 over 100 is greater than 0. Okay? If A and B are both positive or negative, then if A is less than B, then B over A is always less than 1 over B. So it's 1 over A. 1 over B is less than 1 over A. So there is that order again. To say if I inverse both sides of the inequality sign, then the bigger number is now a smaller number. Okay, when I invest. So if I've got A here is smaller than B, but if I invest, B is now smaller than A. So a big denominator means a small number. 1/4 is smaller than, 1/4 is bigger than 1/10. That's what you are saying. 1/4 is bigger than 1/10. So a small denominator means a big number. A small denominator means a big number. A big denominator means a small number. 1/1 billion is smaller than 1/1 billion is smaller than 1/10. Okay, that's what I was saying. Then completeness property. So natural numbers can solve inequalities, equations like this one. We are able to find a precise x to solve such an equation. Then integers help also us to solve such an equation for x. Then rational numbers help us to solve such equation like x squared is equal to 2. Real numbers. So you can see now that from what we've discussed, you can see now that natural numbers are a subset of integers. Integers are a subset of rational numbers. Rational numbers are a subset of real numbers. So it means in real numbers, we find integers. All integers are found in real numbers. All rational numbers are found in real numbers. All counting numbers, natural numbers are found in real numbers. So all integers, all natural numbers are in integers. So integers are a subset. Counting numbers are natural numbers are a subset of integers. Integers are a subset of real numbers, of rational numbers. Rational numbers are a subset of real numbers. Okay, so there's that completeness. And then, okay, I have to record this in 40 minutes. Okay, let's talk about intervals. An interval now is a range of numbers. A subset of a real line is called an interval. If I've got two numbers, an upper number, an upper bound and a lower bound, then between those numbers, I form an interval. Okay. Some intervals are just specified by a number, by just one number. And such intervals are called an infinite interval. For example, x is greater than -2. I'm talking of numbers like -1, 0, 1, 2, 3, 4, 5, going upwards. You can see there are infinitely many elements in that interval. And that interval is called an infinite interval. Okay. Then some interval. So geometrically, when I talk of an infinite interval, we are talking of a ray on a real line or a real axis. Then we also have a finite interval. Finite interval is now an interval like from 3x being a number from 3 to 6. This interval, between 3 and 6, there are infinitely many numbers. It's not a finite interval in the sense that there are finite numbers. Numbers between 3 and 6 cannot be counted. They are infinitely many. But it's called a finite interval in the sense that these numbers, there's a lower bound and an upper bound. Okay, so it's called a finite interval. Then when you represent this geometrically, it represents a line segment on a real axis. Okay, like this one from 2 to 8. These numbers between 2 and 8. Between these two numbers, they are infinitely many, but it's called a finite interval. Okay, then we have intervals now can be precisely be explained in terms of an open interval, a closed interval, or a half open interval. Okay, so we have got an interval like what we call an open interval. An open interval is written like this. This is how we write an open interval. You put a bracket, a curly bracket, A dot B. Close that bracket to represent an open interval. And in an open interval, we are looking for all sets of points between A and B, but not including A and B. So when you are to write that mathematically or using inequalities, we write A less than X less than B. Can you see that in this interval, A and B are not elements of this interval? So it's called an open interval, and we write that using closed bracket. Unlike a closed interval, which we write using square brackets to say square bracket A dot B, then close with a square bracket. When we are writing a closed interval, we are saying A less than or equal to X less than or equal to B. And the numbers A and B, which are the boundaries of our intervals, are also part of that interval. Then when A and B are part of that interval, because there is less than or equal to, we call that a closed interval. And when A and B are not elements of that interval, we call that a closed interval. Are we together? Then we also have a half open interval. A half open interval now, it's closed on the other end and open on the other end. Are we together? Like, okay, this one, we write it like this. So when you're writing a half open intervals, we write this, like for example, if I've got a square bracket, A dot B, and then a closed bracket. This is a half open interval. It means A is part of the interval, but B is not. So when you're writing that, we say A less than or equal to X less than B, which means A is part of the interval, but B is not. Again, we can have a half open interval, which is written as A close bracket A dot B, which is written like this. Okay. So when we are writing such intervals, we usually put circles. We usually put circles and shade when that number is part of the interval. But some intervals are infinite intervals. Now, infinite is not enough. Infinite means we are counting going upwards, up to whatever number that's up to going upwards. So when we are representing infinite intervals, we don't put a closed a square bracket where there is an infinite, but instead we put a curly bracket like that. Like for example, if you're saying A is less than X, it's denoted by this when you're writing it in interval form. Then the same thing, A is less than or equal to X. We write it as A dot infinite with a curly bracket. Similarly, we have got minus infinite to B. We write it like this. This interval, we write it like this. So we write it like, what is that? We write it like this. Then minus infinite to B, we write it like this. Okay, so you see where there is infinite. It's infinite or negative infinite. We don't put a square bracket because infinite is not a number, or negative infinite is not a. So where there is infinite here, we always put a curly bracket, showing that infinite is not a number. So geometrically, we are talking of -2 going there, 8 going there. Okay, how can you write that as a? So we can use this to solve inequalities now. I'm not going to teach you much on solving inequalities, but you know the rules of solving inequalities from your A-level mathematics. Inequalities are very easy to solve because we are just applying our properties of real numbers. For example, when we are solving this number, we just have to know that here now we are now applying those properties. We know that we want to remove this -1, so we add 1 both sides, and when we add 1 both sides, the inequalities remain, inequality sign remain. At O level, A level, we were used to be told that you take this minus 1, crosses the bridge going there, and it becomes plus 1, something like that. But here, we are now applying the properties to say we add 1 both sides. And remember from the property that we discussed above, when you add a number C to both sides of the inequality remains the same. So when you do that, we are left with 2x is less than x minus 2. Then when we take x going there, still the inequality remains because we are adding the same, we are subtracting x both sides, and then the inequality will be just the same. That's where I said if you've got $1 and someone has got $3, if I give you $20, both of you, the amount of money that we have, this one with the dollar still we have less money. Okay, so here we are subtracting x both sides. If I subtract x, I'll be left with x less than 4. So this is the solution. The same thing, what value of x is this one? Here we need to expand the bracket first. 3 times 2, 3 times minus x, then we are left with that. Then we solve the inequality, taking x, adding x both sides, we are left with 2x, simplifying that, 6, subtracting 6 both sides, then you are left with that. So the solution to that is x is less than 2, less than or equal to 2. Okay. Then sometimes we've got a quadratic inequality like this one. Since we are multiplying 2 brackets and we are getting a number which is less than 0, a number which is less than 0 is a negative number. When do we get a negative number? You can only get a negative number when you are multiplying 2 numbers with different signs, the other one positive, the other one negative. So we need to consider some cases. A case that this bracket is positive now, and this bracket is negative now. Since we are multiplying 2 numbers and we're getting a negative number, it means the signs of these 2 numbers should be different. So we consider the case number 1 that this bracket is positive and this bracket is negative. When this one is positive, this one is negative. When you solve this one, you come to x is greater than 4 and x is less than minus 2. By looking at this, we cannot get an x. A number which is bigger than 4 and at the same time is less than minus 3. It's impossible. Therefore, this is wrong. So it's impossible. Then we consider the other option, case number 2, whereby we're saying this bracket is negative. Because remember, initially on case number 1, you say this is positive. Now we consider this one is negative. This one is positive. When you solve that, we get x is less than 4 and x is bigger than minus 3, which forms an infinite range to say x is between minus 3 and 4, which is possible. Then this becomes our solution. Then we can also solve inequalities with fractions. Here we just need to make sure we know that we don't know what is x. So when you're solving such an inequality, it's important to square both sides so that when you're multiplying, we know that you are multiplying with a positive number. That's another approach that you can do. You have to square this thing and square this thing, then we know that it's positive. Otherwise, when it's like this, you cannot just multiply it because we don't know whether it is a positive number or it's a negative number. Absolute value. An absolute value means the positive value. An absolute value means when I'm talking about the absolute value, it's also called the magnitude of a number or the size of a number. When I'm talking of a magnitude of x, its magnitude of x is x when x is positive and is minus x when x is negative, which means the modulus or the magnitude of minus 6 is 6. The modulus of 5 is 5. The modulus of 0 is 0. So when the number is negative, you multiply this number by a negative to make it positive. Or you just take this number only. So magnitude of minus 15 is 15. So in the definition, magnitude of x is minus x when x is negative. To mean if I'm saying magnitude of minus 6 is minus 6, which is 6. Okay. So magnitude, we are just looking at the absolute value of that, or the number without its sign. When it's positive, it remains positive. When it's negative, you just drop the minus and write the number only. Properties of absolute values. Absolute values are always greater than 0, are greater than or equal to 0. Okay, which means we don't have a negative of an absolute value. Absolute value of a real number is always non-negative. Absolute value of a real number x is 0 if and only if x is 0. So there's only one way of getting the absolute being equal to 0, only when x is 0. So when you get the absolute being equal to 0, it implies that x is equal to 0. And in general, if y and x are any two numbers, then the negative absolute of x is always less than or equal to the absolute to x, and is always less than or equal to the absolute of just a positive x. Absolute of minus x is always equal to absolute of x, and absolute of x minus y is always equal to absolute of y minus x. So the difference of two numbers, the absolute of that is always the same. Absolute of x is always equal to absolute of y. So absolute of x is equal to absolute of y. It implies that x is either equal to plus or minus y, because y can be a positive number or a negative number. So if they are equal, it might mean that y is the negative of that. Then absolute of x times y is equal to absolute of x times absolute of y. Absolute of y of x over y is always equal to absolute of x or over absolute of y, provided that y is not equal to 0. Absolute of x plus y is always equal to, is less than, not always equal to, absolute x plus y is less than absolute of x plus absolute. This is called plus absolute of y. This is called the triangular inequality. For any a being a positive number, takati absolute of x is equal to a if and only if x is equal to plus or minus a. X is less than a. Absolute of x is less than a. It also means that x is between minus a and positive a, is between that range. If absolute of x is greater than a, it means x is greater than a or x is less than minus a. Like for example, if I say 2 and 7, okay, if modulus of 2 is greater than 7, then it means that 2 is bigger than 7, or it can be a negative version of that. Absolute of x is less than a. It means that x is between minus a and a. If absolute of x is greater than or equal to a, then it means that x is greater than a or x is less than a. Then we have, for any two real numbers, absolute of minus x is always equal to absolute of x. Can you show that this is the proof which shows that absolute of this? So when we are showing this, we say, since x is an element of real numbers, then x can either be positive, which means it's greater than 0, or x can be 0, or x can be negative. Then we consider these three cases. If x is positive, greater than 0, then minus x is less than 0. Okay. So if x is positive, then minus x is now less than 0. Thus, modulus of minus x is always equal to minus x, which is equal to x, which is equal to modulus of x. That is minus modulus of minus x is equal to x in that case. Then if x is equal to 0, it means modulus of minus x is equal to modulus of minus 0, which is equal to modulus of 0, which is equal to 0. Then in that case, modulus of minus x is also equal to x. Then when x is negative, we know how to find modulus of x. Then minus x is less than 0. Then modulus of x is equal to minus x, which is equal to minus modulus of minus x, since x is positive. Therefore, modulus of x is equal to x. Therefore, in all the three cases, modulus of minus x is equal to x. Then we've shown that modulus of minus x is always equal to modulus of x. Then solving equations with absolute values. When you're solving equations with absolute values, when we have got such an equation, modulus of minus 2x plus 3 equals to 7. It means you consider the positive 7 and the negative 7. That's what it just means. So you have to solve two equations. 2x minus 3 is equal to 7 and 2x minus 3 is equal to minus 7. So if we solve these two, you get two solutions. And these two solutions are both the solutions of such an equation. So when you're solving inequalities with absolute values, it means you take a range of values. In other words, you just come up with two inequalities. If you've got 5 minus 2 over x, modulus of this being less than, it means you just take the minus of this one and the plus of this one, which means this inequality is between those two values. So what it means is we are saying to remove the modulus, you just say from minus 1, the negative of this number, from minus 1 being less than 5 minus x over 2 being less than 1. These are the properties that we talked about under properties of modulus. If you go to the properties of modulus above, these properties that we are talking about, these are now the properties that we are now applying. These ones above there, where are the properties? I can't find the properties of that. These are the properties that we talked about, properties of absolute values. This one that we're talking about. Okay, we said if modulus is less than a, then it means if modulus of x is less than a, then it means that minus a is less than x is less than. We are now applying these properties to solve inequalities with absolute values. Okay, so this is how we solve inequalities with absolute values. So when you're now solving such an inequality, with the inequality, this one, you now consider, you now have to, we want to remove this 5, so we subtract 5 both sides, minus 5 there, minus 5 there. Another way is to separate, take this inequality first and solve it, this inequality that I highlighted, and solve it, and then take this inequality and solve it, and combine your solution if they can be combined. Alternatively, you can solve these two inequalities once, like what we are doing here. Just add 5 both sides, subtract 5 both sides, then this 5 disappears. If I subtract 5 here, I get minus 6. If I subtract 5 here, I get minus 4. Then we have got that multiply by a negative both sides. If I, okay, or you can just divide by minus 2. If I divide by minus 2, my inequality sign have to change. So if I divide by minus 2 here, I get 3. If I divide by minus 2 here, I get 2. Then the inequality sign we have to change. Remember the properties of negative numbers, a number that we discussed. Then I now have 1 over x here. We also talked about the properties of inverse. This now disappeared. Okay. We know that we discussed 1 over a. If a is less than b, then what about 1 over a and 1 over b? That's what we are doing. We are just inversing. So if you inverse, the inequality sign changes. So if I've got 1 over x here, it means if I'm inversing this, you have to, this inequality sign have to change. So I now have 1 over 3 being less than 1, x being less than 1 over 2. This is now the solution of the inequality. Okay. Then if I'm solving this inequality, I also have to take this from minus 1 to 1, then remove the modulus, then solve this, then I get that inequality. The same way, if I'm solving this, I take that's b, then this now solution can be written using the interval notation that we discussed. This is now n, a closed interval, like that. Okay, you can write that as a closed interval. If it's an open interval, you can write it as an open interval. Then if I'm solving this, then I solve it by taking from minus 1 to 1, like that. I can solve that as 1, or I can separate that. Then you can see now this interval, these are two separate intervals. I'm saying x is greater than 2 and x is less than 1. So the interval now, I can write it as 2 interval from minus infinity to 1 and from 2 up to positive infinity. Okay, then you try to solve that one as well. That's the first lecture, which I'm going to say. I have to make the lectures less than 40 minutes because this platform only allows us to do a lecture up to 40 minutes. So let me end the first lecture here. When we meet in our next lecture, we are going to discuss the principle of mathematical induction. This is just an introduction. I hope you are following and you're understanding. Thank you.